So the subject is opening the black box, explaining supervised advanced machine learning models. When we speak about AI, machine learning, statistics, we have to make precise definitions what we mean. Someone said AI and mean machine learning. Someone said machine learning then mean statistics. And someone said we need data scientists, and actually means BI expert, as Tal said before. So I have to explain what I mean. So first of all, explaining. What is the meaning of explaining machine learning models or AI? I think that you see in my presentation and the other presentation that I think that each presenter means something a little bit different when he speaks about explainability. So I will define exactly what I mean. And you may assume, you may ask what is advanced machine learning models. So what I mean is, in my presentation, is analysis of predictive models based on noisy data, not pictures, not video, not voice, not language. And so you may assume that I will not speak much about deep learning. I will speak mainly about data, classical data, which we have many dependent variables and independent variables. We have a dependent variable, independent variables. We want to develop some model which predict the dependent variables with the independent variables. You may see that during the presentation, I changed the notation. Later, I will say target and features. But now I start from the statistical terms. So when I said advanced machine learning, so I mean data for predicting from large database, big data, cross sections data, predicting one variable with quantitative other variables in the data set. You might assume that if we said opening the black box, that it's very difficult to explain those models. And you might assume that maybe there are other models which are not complex and also not difficult to explain. Do you know such a models for predictive modeling? No? Simple model. Decision tree, well, might be very, very easy to explain. But it depends what is the meaning of explain. So let's go. Just a few words about me. I'm the CEO of GStat. We are leading data science and AI service company in Israel. We have, as of this morning, 205 data scientists, analysts, big data integrators. We have 20 years of experience. We did thousands of predictive modeling during the last 20 years. And we expertise in big data analytics, machine learning, and generally value creation from data. This is our area of specialty, machine learning. We have a software company which develop automated machine learning software. Most of you, I think, have experience with it. If you are using supercell coupons, this is a result of our systems, but it's implemented in many other large organizations. Big data, risk, fraud, credit scoring, financial risk, and marketing area, segmentation, marketing automation, advanced analytics. We sell also BI tools like Tableau. This is a lot of satisfied customers with machine learning success stories in each one of them. Okay. Simple models which can be explainable as I will define it, are the classical statistical models. This is an example of output of linear regression. Dependent variable is the level of cholesterol. Dependent variable is time TV, the time that observation, that person see maybe in hours TV, and a constant. So this is the usual, I think, known to all of us from the first year, from introductory statistics. So what are the characteristics from the point of view of explainability, as I see it, of linear regression or classical statistical models? First, it's based strongly on probability theory. So once we are doing linear regression, logistic regression, we can do hypothesis testing, quantification of the effects of independent variables by the dependent variables. Very easy, very straightforward. Here we see that the number is 0.044. What is the meaning of the number? The meaning of the number, it's the derivatives. If I see one more hour, how much it will increase my cholesterol levels. This is very transparent to the experts, to all those who want to understand the results, and maybe to those who want to do something with it. For example, to make prediction. We have what will be if we change the number of hours that we see TV, we watch TV, what will be our cholesterol level. So the classical statistical models, like linear regression, usually they assume that the dependent variable depend on linear combination of the explanatory variables. And once we have it, we have a very closed analytical formula for prediction. Plug in the values of some subject that you want to predict the Y, plug in the X, and you have predictions, you have significance level, etc., etc. So we have a lot of tools to understand, to analyze the model results. We can see the relation. Relation is linear, and it's globally linear. So it means that it doesn't matter which observation I see, the effect is linear. So very, very easy to understand. Maybe we think that there is nonlinear relationship, so we can add polynomial relationship, and then we can see that nonlinear relationship very easy to explain and to make statistical hypothesis testing, etc. So for me, explainability is the ability to take the model results, like in linear regression, and to understand what are the relationship, what are the analytical relationship between the dependent variables and the independent variables. So, and as a practitioner that work with hundreds of projects, I'm asking all the time to explain models. So here it's very easy. And this is what I mean, model that can be explained. So I define this because now, later we will ask when we have difficulties and which kind of models we have difficulties to explain. If we explain models, not only prediction, but we can do optimization. And this is very important because in advanced complex machine learning, we have a lot of problems to do optimization. Suppose we have a reactor in industry. We want to optimize the level of the pH and the speed and temperature. We classically develop models, maybe polynomial model, then do some optimization subject to constraints, And that we can do with models that are very explainable. This is the inventory of models. I think I used all of them. And they have in common linear in parameters. We can understand the relationship. We can calculate derivatives. And also, if we want, we can also do some interaction or polynomial analysis to take care about some kinds of problems. This is the same also for time series analysis. Again, linear in parameters. We can do predictions if we have estimates. We can do simulation, focus the future based on those models. Very easy. Very easy and very transparent. Okay, so this is the classical statistical models. This is the way that I have started my career in the 80s. In the 80s, I developed predictive models, what is called today machine learning or data science. But I did it with linear regression, with logistic regression. And but in those years, we've started to see many new cross-section data coming from operational systems. Those data were not the data that we used to analyze from control experiment or macro time series data. When we analyze the data, we see a lot of problems. High percentage of missing values in big data, cross-section big data, or panel data. We started to have, instead of 5, 10 variables, features, we have started to have hundreds, maybe 500s. So the mission of variable selection by stepwise, backward, forward, become very, very complex. Data includes many outliers. There were difficulties in identifying nonlinear complex relationship, identifying complex interaction, and most of the data sources are observational data, not results of controlled experiments, with a lot of problems how to tackle with this. And I think that maybe all the problems here, we have solution. This yet, we don't have solution. So what happened in the 90s, started to see new models, new algorithms, which aim to deal with those problems of outliers, of interactions, of nonlinearities, missing values, better than the classical statistical models. Of course, the best model is the decision trees. Very easy to implement, very easy to understand, and to explain. But there was the neural networks that we have started to use in the 90s, which were very complex to explain if we have many layers, not one layer. If it's one layer, it's linear regression or logistic regression, depend on the problem. And we have the SVM, which was quite difficult to be used and to understand. But there was new modeling technique to deal with the large databases, cross-section databases that we have to analyze for our clients. This is something Leo Breiman wrote in 2001. I read it about 2003 or 4 and to reflect my feelings. He said, there are two cultures now in the statistical community. One focused on modeling according to the classical models, and one tries to solve all the difficult problems that we have with the actual data, big data that we have now. So then, he didn't call it machine learning. Why didn't call it machine learning? Because the term was not available. It's only in the last 10 years that we start to speak about machine learning. But this is what exactly he means here. He means we put X into unknown black box, receive Y, and our target is to receive the best Y, the best prediction based on the data. And if we don't have data which under the classical assumption of linear regression, it doesn't matter. What is matter is the prediction, the predictability of our algorithm. And now comes the question, he calls it two cultures. Comes the question, what is statistics and machine learning? So statistics, we said, it's based on probability theory. We have closed formal models that we can use for predictions and we can use for optimization. In contrast, machine learning, we use general purpose learning algorithms and helpful when one is dealing with wide data, as I said. And machine learning makes minimal assumption about the data generating system. So we don't care about the data generating system, about the probability model. We want good prediction. So Michael Jordan was in the conference, last conference of the Israel Statistical Association, and said there is no difference, everything is statistics. Well, maybe, but this is the distinction that I make. If you based your model on classical statistical and probability models, then I call it statistics. If it's only focused in prediction, then I call it machine learning. And then, during the last 10, 15 years, better machine learning algorithms for super predictive models. The first version, the first stage of neural networks was very poor in prediction accuracy. It's only after the deep learning revolution, which was 2003, 4, 5, that it starts to shine in the problems of video, picture, etc. So it was not very good, and decision trees was very explainable, but was very poor in performance. So what happened is that the statistical community, statistician, developed the basis, the basic models that we are using today for predictive analytics in the area of machine learning. It's started with that Leo Breiman, the random forest. What Leo Breiman did, he said, instead of taking one tree, let's take the idea of bootstrapping. We have many, many trees. Then we do voting on averaging, and we receive till now one of the best performing models, the decision trees. Later it's come to the boosting. It started with AdaBoost. AdaBoost. The idea was, again, to make many steps, each little step, and then going on. But here, we all the time try to improve the errors from the last stage. And this led, of course, later to the XGBoost, or CutBoost, and all other boosting methods. Later, maybe as a result of Kaggle competition, we see the bagging and boosting and stacking, which means that we take a few models and we run and make the best models of decision trees or XGBoost, best models of SVM, best models of deep learning. We have prediction for each one of them. Then we develop second-level algorithm to see the optimal weights for making the best prediction. And also, we have new software tools which support all the process. I think most of you know the sklearn in Python. You don't see p-values, significance level if you are running sklearn. even if you run logistic regression, because this is not the aim of the package. The package is focused in prediction. This is an example of the results. So this is a credit scoring problem. We have logistic regression, random forest, gradient boosting, deep learning models. The logistic regression, the AUC, is 0.84. For random forest is 0.99. For gradient boosting is 0.99. And then there are the models of deep learning, which, as I said, are not performing as well as random forest or boosting. So we see that we have a huge benefit if we use for big data and large cross-section data new methods for predicting. So where we are now, we have the new machine learning models, complex models. We have automatic feature selection. They treat very well complex interaction. They treat very well missing values, nonlinear relationship, outliers. And the result is usually better prediction accuracy in large and noisy big data. Sometimes in small data, we don't observe that they are better. Sometimes it's better to run linear regression or logistic regression if we have small data. But where we are now, no transparency. If we want to learn from the model what to do, what are the relationship, what is the shape of the function that relates the x's to the y, we don't have any tool. We didn't have any tool to do it. We cannot do classical scientific research. Suppose we want to make a research on a new healthcare procedures. So we want to present the results, but no one will look at it, because if we cannot explain to those who order the model or to the regulator, we cannot use the models. If we cannot explain it, we cannot use it. This is the same in the financial sector. If we want to develop models of credit scoring, we are not allowed to use advanced machine learning models, even if we know that they give better prediction. And the reason is the regulator said, 2008, the financial crisis was a result of statistical and mathematical models that no one understands, and companies manipulate the models according to the profit targets. And because no one understands it, there was a global financial crisis. So you are not allowed. So many speaks about credit scoring, but if you are going to the regulator and said, I have a wonderful model for predicting who will be defaulted, you cannot use it. The same in Europe, the same in the United States. The same for healthcare. You cannot say, okay, I did something with a new medicine. I have a model that predicts ABC. You cannot use it. So this is not to say that advanced complex machine learning models don't have some basic tools for understanding. If you are running a model, an XGBoost or deep learning model, you receive something which is called variable importance. Variable importance is based on some measure. For example, if you have a random forest or XGBoost, how many times a variable exists in splits on the whole trees. So in that model, we see that there is a variable which exists a lot of times, so E is the most important. So we can rank them, and we can have some clues about what's happening. But what we cannot do, we cannot understand what are the direction of the relationship, whether it's a positive correlation, negative correlation. What is the shape of the relationship? Maybe nonlinear. We don't know, because it's very complex. There's many trees, averaging of many trees in random forest. We cannot go back and see exactly what is going there. So this is not enabling us to explain model. Yes? Yeah, there are some measures like reduction in the likelihood or some other. But again, the results is like this. You can set which measure you want to base the variable importance analysis, but it doesn't tell you whether it's positive correlation. Yeah, this is a method. This is a method the regulators recommend. They said run advanced complex models, machine learning models, see what are the important variables, implement. But there is a lot of interaction. There is a lot of nonlinearities, and that direction is not satisfied if we want to understand what's happening inside the models. So here we come to SHAP, the third time today. So, but I think I present it from my point of view, which is different from the point of view that we saw before. So this is Scott Lundenberg, PhD candidate in computer science at the University of Washington. I think I did it a year ago. I checked, he didn't, yet he is not a PhD, but he did a wonderful job. And the job as described in the former presentation, I have data, I have model, I have prediction formula. I can use the prediction formula to try to explain the results with some method. The method is called SHAP. What is the idea, the intuition behind the SHAP? So my colleagues mentioned it. It's try to take points, observation, in the multidimensional space of the observation of the features, and to run a simulation of the prediction around the observation, the point around the vector x. We change around it in some smart way. And then we can run linear regression against the simulation of the data around the point. And then we receive some, we receive the intercept or the effects of each variable for that specific observation. So this is the basic idea. We take a random sample from the space of the observation, maybe 3,000, 4,000, 5,000, 10,000. For each one of them, we do that linearizations in the area of the point. After we did it, we have a prediction model for each point based on the values of the vector x of that point. So if you have 3,000 observations, we end with 3,000 effects. Suppose age affect the y, let's say wage, hourly wage. And dependent variable of feature is age. So we have 3,000 observations, each one with different age, which show the effect of age on wage. I want to correct Irad. He said that that method is global method. What he said is we average the 3,000 points and we have a global measure for the feature. But the strength of SHAP is not to do the averaging, but to analyze the data as it is. And we will see how we are doing it. Well, as he said, as my colleague said before me, it's based on shape term from 1951. How do we make coalitions? So the features come to the coalitions and start to do different coalitions. And then the value of the one that entered the coalition after former n variables inside is the improvement in the target function. And when we look at all the possible coalition for a specific variable and we average it, we receive a value which is called sharp values, which reflect the effect of that feature on the dependent variable, the phi. So this is the formula, and then we receive it. What Lundenberg showed is that that method have three good properties. First, local accuracy. The sum of the feature attribute is equal to the output of the model we are trying to explain. So doesn't matter which way we go. We have 3,000 vectors x. For each one of them, we do simulation around the vector x. We calculate according to that formula, and this will be the properties. Missingness, features that are already missing have no impact. Consistency, changing a model so a feature has larger impact on the model will never decrease the attribution assigned to that feature. So what he showed, the sharp have those properties, and only sharp values has those properties. As Erad said, the calculation is huge. We take 3,000 observations. We maybe sample some thousands of observations around each point, and we have to calculate this. Very difficult. So what they show on the paper that we can approximate these results of sharp values with a weighted regression, with a specific kernel. So for each point, we have specific kernel. We run the regression according to the kernel, and then we receive the sharp values. So this makes it's still very challenging from the point of view of calculation, but it's possible in my laptop. With some hundreds features, I run it on 3,000 points, vector x. So there was sampling around each of the 3,000, running linear regression for each point, and it's take maybe less than a minute. Another point, which Erad, to mention again Erad, he said that there is no treatment of interaction, but there is. And this is the way that it is done. You do it the same way. You take two variables together, you look at them as one variable, and then see when you took the two and enter the two, what are the effects, the sharp values if you enter them and remove them. And then we can calculate, as we are calculating in regular regression, the interaction effects, the metrics of interactions, which is, of course, might be very huge, because suppose we have in the model 1,000 features, so the correlation is 1,000 over 1,000. So there is a lot of calculation. When I run this on 3,000 observations, it takes about 30 minutes in my laptop with 8 gig of memory. But we can do it. And then after we calculate the interaction effect for a specific variable, so we run that variable I with j, I with j plus 1, I with j plus 3, all those combinations. We receive the interaction effect of the variable I with all j, with all the other features. And then we can calculate the main effect as the effect that we receive from the stage 1 of SHAP values, linear regression, simple linear regression without interaction, and we subtract all the interaction, we receive the net effect of the variable I. Net effect. This is net effect, but it's changed according to the value of the interaction. I will show you in a few slides demonstration. So how the SHAP output is looking like when we run SHAP. First of all, SHAP is the best practice today because it's integrate the Lime and many others as a simple cases of SHAP. It's implemented in XGBoost. If you are downloading it to Python, the API, you have commands inside the algorithm to do SHAP. You don't necessarily have to install SHAP. And I think it's the same with R. So how SHAP is looking like? So we have observation, specific observation. There is a general intercept, the general bias. Someone can explain me why in machine learning they call it bias? Bias. Bias, it's bias, not intercept. Okay, so it's the bias. Now there is the main effect that we receive by the local regression for that specific observation. So we have the main effect. When we do also interaction analysis, we have the main effect over the main effect after we subtract for the main effect all the interaction effects. So it's very mind analysis of variance, the way that we run analysis of variance. But there is a huge computation involved there because you do it for each observation, maybe hundreds of dependent variables. You sample from the prediction model points around the point. And well, as I said, 3,000 observation with 100 maybe more or less. It took about half an hour. So now, if you understand, I hope something, maybe after the third time, what is SHAP, I want to demonstrate it on the data we did in GStat, the workshop on that area, because why we did it, we want to push our clients to use advanced models. And many clients, we have a problem because they want explanations. So we have decided to push it by doing a workshop to about 20 employees, which learn how to do it. So, so we use Central Bureau of Statistics data. This is the Israel Household Longitudinal Survey. If you don't know, there is such a survey. It's running from 2011 to 2018. I think, no, there is data till now, each year. There are some problems, but it's a wonderful data source if you want to learn about the dynamic and transition of the Israeli population. They've started with 8,000 households, with all the members in each household. Of course, each year there are less. I don't know if there are new each year. Or so maybe, so we are close to a point where we have to make a new. Okay. Okay. Because each year we have less and less households or persons. So what we did, we took the personal data for each person in the survey include for each year the gender, education, wage, housing, language speaking, Eretz Aliyah. So hundreds of features which we want to analyze and to correlate with important variables for the Israeli society to understand the mobility of the Israeli persons and households. So what we did in the laboratory was analysis of the relationship between wage, labor force participation, wage quartile, Asiron, with personal characteristics by using XGBoost as the complex model, and SHAP for explaining the relationship. And when I mean explaining, I want to see if age change, how my wage change. This is what I received when I did research, and I did on Israeli, on the wage of Israeli employees, and I know the results. So I know what to expect, what is the shape of the function of the wage function relative to age over the life cycle. So we did a lot of analysis. I just show you some data to get some impression of what we have there. This is a transition metrics between 2013 and 17 of labor force participation. We see that those who participate in labor force in 2013, 73% still was part of labor force participation and 27% moved from the labor force participation. For those who have worked, 87 still were, and 0.13 left the labor force participation. So this is some kinds of data that you can do XGBoost model with logistic regression or softmax. Someone can explain why softmax? Okay. In all the algorithms, it's called softmax function. So you can run logistic regression and see, according to age, wage, profession, etc., what is the probability that you will left in a few years the labor force. This is the wage, hourly wage. Each of these boxes show distribution in each year of the hourly wage of those who participate at the survey. We can see the dynamics of increasing during the years of the wage. And what we were interested in was in two things. First, analyze the distribution in point of time, how the hourly wage depend on age, gender, etc., and what can we predict what will be your wage 5, 6 years from now. So there is a lot of questions that we may ask about that model. This is the distribution of our wage between 2012, 2007. And this is another thing that we did with softmax, multinomial regression, in which we try to predict based on your quartile group today, Siron Achnasa today, with where you will be in 2013. You were in the sixth quartile, where we will be in 2017, and we can see the transition of the Israeli population. And want to see how is it for higher education, how it is for master degree, how it is for women, how it is for Olim Chadashim, how it is for different group of population, and not doing it in the classical research methods as we did traditionally. So again, I will show you some results. of the sharp values analysis and what we have found. So this is again for each variable, for each observation that we analyze, where the Hall effect, where the net effect, and where the interaction effect. Okay, this is the sharp values for the age. So what we have here, we have 3,000 betas for each person. We have different beta of the effect of the wage effect, the sharp value. But when we look at it, the sharp values against the age for the sharp values that we have at the output, we see very clearly the regular shape of the wage functions that we have found in many research in Israel and in the world. The wage increasing till about 60, and then it's increasing and then start to decrease. When I did a research on that area, what I did was I put on the regression age and age square, and I received such a graph, an hyperbola, which was like this. So the difference here is that we don't have global relationship. We have something that we can try to find the average, but there is effects which are results of random effects, and maybe the interaction effects. This is without the interaction effects. Here it's with the interaction effect. So this is the net effect. There is randomness here because there is randomness in the data, but there are other variables interacting with each point. Each point is different ticks, so we see it. But we see that there is something here, that most of the data is here. So maybe if we run linear regression, cubic regression, we receive something here with maybe significance level like this. This is more noisy because this includes the interaction effects, and this is the net effect. So this is things that we have from sharp analysis. For me, it's very satisfied as a research tool or as a tool to go to, I don't know, some public agency to make decisions based on it. Today, once we are going to agencies to do research, they will not receive this because some statistician said, what is this? I don't know what this is. So I think that it's very promising what we've found. This is interaction effect. We plotted the sharp value against age, controlled for you speak Hebrew or you don't speak Hebrew. And we see different graphs. Why is it? Why is it? This is Hebrew speaking. This. What is non-Hebrew speaking? Those who get 15 mandates today. So they are not going to the army. So the sharp value in the 20s are higher. But later, the Israeli young have low sharp value, but when they go to and start to be part of the labor force participation and finishing their studies, those who don't speak Hebrew, the sharp value is very low relative to them. Now, again, if you ask me, I can do research with those results. I can present them. If the referee in some journal will don't throw it away, and this is what usually they do today, because they want statistical classical analysis. The last thing is I did here some step function, classical regression, and the question that I ask, I'm a practitioner, I'm not a researcher, I did it for GStat laboratory. Can we do some probabilistic analysis on that data? Let's recall it. And maybe we have more strong basis to base research and developing models in regulated areas based on those models which we know that they are better. Thank you. We are hiring more than 40 open positions. All those that will not work with the TAL can come to us. And thank you.